Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components, the related technology, and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yes, thank you, Paul. What I'm going to talk about today here really is a history of the development of the Wilkinson divider. I think part of what you're going to see here is that the divider did not, the Wilkinson divider did not come in one fell swoop. It's managed of iteration of designs and concepts that led to the divider that we know and love today. I'll start off by talking about some advantages of the existing Wilkinson style divider, and then we'll kind of walk through the development of those advantages as the technology developed. Like I said, basically talk about sort of the history and who contributed to this sort of state of the art, and then we'll summarize it up and talk about some TRM differentiators.
Well, thank you. And maybe to get started, what did people use prior to the introduction of the Wilkinson Power Divider?
Sure. So basically, prior to the Wilkinson Power Divider, most of the designs were based on ring hybrids, or other sorts of devices like that, and being used as a power divider. So the end result of that is that these all had very narrow bandwidths. They really are only good for 15 or 20% bandwidth. And a lot of the manufacturing technologies that were used previous to the development of the Wilkinson really had to do with sorts of manufacturing technologies that were not very repeatable, difficult to manufacture, and very expensive to manufacture, quite frankly. So they were really, things could be done, but it wasn't really very easy to do it, and its performance was quite limited.
So what were some of the specific advantages of the Wilkinson then?
Sure. So the Wilkinson, right now, the way that we currently exist is we have very good VSWR match on all ports. We have good isolation between the outputs. It is essentially a lossless device. We're basically just looking at ohmic loss of the copper right now. So it's very low loss. It can go for very, very broad, very broad bandwidths. You can easily achieve 10 to 1, 20 to 1 sorts of bandwidths using the current technology, which is octaves and octaves above the 20% bandwidth of the previous art. It's also very manufacturable with printed circuit technology that we currently have today. These can be manufactured in volume and have their performance repeat quite well. There is a downfall of the Wilkinson divider, and it's only when it's really used as a power combiner, which I've spoken about in the past. And that is that basically the isolation resistors that are in the design, since they're in a balanced mode where they're sitting between 2 traces as opposed to going to ground, you don't have a good thermal path getting out of those resistors. So when you're using these dividers as a combiner in a non-coherent situation, the power handling capability is limited. And that is really the only downside of the divider. But for many, many applications, it's a wonderful device and does a great job.
Okay, well, thank you. Now, you had mentioned something about the history associated with the Wilkinson divider. Could you share some of the details?
Sure, love to. Basically, the original paper for that Ernest Wilkinson wrote, it was published in January 1960. Really, I think, but you have to think about what it was that Ernest had to work with when he published his paper. So we have to go back a little bit in history before his paper to really understand and appreciate the significance of his contribution. So really, the first thing you need to do is you need to have a transmission line. If you want to go way back in history, you can't have the power divider unless you have a transmission line to carry it. So going way back in history, you look at really, coaxial line. We think about coax as being around, literally forever. It was first proposed by Heinrich Hertz back in the 1890s. Really came into being used in the 1930s. Waveguide, which is another technology that we look at as far as being a common technology, wasn't publicly demonstrated until 1936, and really the coaxial slab line sort of strip line sort of configuration was first developed back in the 1940s. So really, this is only 20 years before Wilkinson published his paper. When we were first developing this basic technology for building a transmission line. So really 1960, although for me it wasn't that long ago, really wasn't that long after the developments of some basic transmission line technology. A little more detail on as far as some of the strip line and microstrip sort of pieces here. If you take a look at the idea of taking a coaxial line and making it into a flat plate separated by two metal plates was introduced by AIL in 1951, and they trademarked the name strip line. Now, the thing that's interesting about the AIL patent or trademark is that it used an air dielectric. So it was really a suspended strip line, not a true strip line as we think about it today. In 1956, Sanders Associates trademarked the name triplate, and that basically used two PCBs with one circuit board in the middle with the trace on it as the cover. Now, this is what we traditionally would consider a strip line circuit as how we would build it today. So this was only trademarked in 1956, only 4 years prior to Wilkinson's development of the Wilkinson Power Divider. And then in 1952 is when the trademark name of microstrip was put out, and that is basically a printed circuit on one side of the PCB as opposed to having it in a sandwich. So really, just a couple years before Wilkinson, all this development was being built on basic transmission line technology to be able to go ahead and actually be able to realize these circuits that Wilkinson would then later on advocate for.
Okay, so once again, were there specific things that people did that brought about the introduction of the Wilkinson, or what was happening right before 1960?
Yeah, so immediately prior to 1960, like I mentioned in the introduction, all power dividers were based on what they called hybrid circuits. And these are all basically rat race ring hybrids, where in order for these to function, you have to rely on a delay line to make the cancellation. Delay line has phase dispersion associated with it, and therefore its effectivity of frequency range for having that phase cancellation is very narrow banded. And it really works quite well. And don't get me wrong, it's a wonderful circuit, but it is limited as far as bandwidth is concerned. We like to think about Wilkinson power dividers as having a minimum sort of bandwidth of an octave. The prior art only had a 15 or 20% bandwidth. So the advantage was significant. I think what's also interesting here is that, and we're going to see this in a minute with the excerpt from Wilkinson's original paper. The original Wilkinson design had the same narrow bandwidth as the existing art. It was just a different way of doing it. And what we're going to see here later on is that later additions to the art gave it its wide bandwidth characteristics that we know today. So the initial paper, as I mentioned, was published in January 1960. The words that Wilkinson chose to have in the summary of his paper that was published in the IRE was that it's a circular symmetrical power divider which splits signal into n equiphase amplitude parts, where n can be odd or even. So he's really looking at his concept was to build an 8-way power divider and have all the power division happen in one go, and make sure that we have isolated ports between them. He was only touting a 20% bandwidth on this initial paper, it's a remarkably clever idea as far as what he did. Part of what's the beauty of this is by putting that resistor in a balanced mode, is sort of the magic that makes this thing work for any number of output ports. So flip over to the next page there, Paul. So this is the diagram as far as to what Wilkinson had in his initial paper. And as you can see there, what he had was basically a coaxial airline construction, and that he was relying on the quarter wavelength line within that coaxial radial structure, and then the internal loads are in a star configuration between all 8 of those outputs. The beauty of this, like I said, is that this puts the resistor in a different mode than the traditional Magic T or ring hybrid configuration, which was essentially the prior art. What this configuration introduced was a straight transmission line configuration that, with some balancing resistors, allowed for an equal power split, depending and is independent of the number of splits that you actually needed. All of the prior art required this feedback loop in order to be able to have the balancing and the isolation actually happen. This design removes the feedback loop, which is in looking back at the design is a very important point as far as the development of the actual design itself.
Okay, and so what came next? The next iteration, so to speak.
So the next iteration happened just 5 years later, and this one over here is essentially now what has happened now is that this particular paper talked about doing this in traditional strip line or triplate, the way that Sanders called it, and what they did was, instead of having the entire impedance transformation happen in one go, which is how that Wilkinson described it, this paper here put input and output transformers onto the power divider. So this way here, the impedance ratio of transformation in the actual Wilkinson divider itself, which is that first section right where the split happens up to that first resistor, did not have to have the entire impedance transformation go all at once. And by putting 2 additional transformers on it, we were able to expand the bandwidth. So now, instead of having a 20% bandwidth, this power divider here now has about a 60% bandwidth by putting these transformers on the input and the output. Isolation bandwidth was about the same, but this allowed for a much broader bandwidth operation. Really, and this is, I think, a very important paper, because I think this is the one that points out that you don't necessarily have to do all of the impedance transformation in one transformer. Now, this paper here talked about, from an isolation standpoint, there was still just a single isolation resistor, the way that Wilkinson described it. But this opened the door for having a multi-section transformer for the full impedance transformation. The other thing also that's interesting about this paper over here is that Wilkinson spoke about having equal power division This paper over here spoke about not only can you do equal power division, you can also put a taper on it if that's necessary as well. So this increased the bandwidth, and it also allowed for unequal power division, which can be very helpful if you're trying to build a feed network for a phased array, for example, where you want to have a Taylor weight across the aperture. These sorts of power dividers work quite nicely as far as actually being able to do that. So for multiple reasons, this was an important paper that was written back in 1965.
Now, is there still another variation to come?
Yes, and this is actually the most important variation as far as I'm concerned. I almost think that we should call the Wilkinson Power Divider the Cone Power Divider based on this paper. What Seymour Cohn did here in February 1968, so this is 2 years now after the previous paper. What he did was supply a full mathematical background for building a multi-octave sort of divider. This is the same kind of configuration that we currently use. What he proposed here was that he can very easily expand the bandwidth of the Wilkinson Power Divider, and by adding sections. And when you add a section, that is a pair of transmission lines and an isolation resistor. What he talked about in this paper here is that for 2 sections, you can get an octave or 2-to-1 bandwidth with very good isolation VSWR. And he gives examples for 4-to-1 bandwidths, again with very good performance, as well as a 10-to-1 bandwidth, which had 7 sections in it, all presented in this paper. It is really this is the configuration that we really use today for most of the math that leads into this. If you flip the page there, Paul, you can see really this is kind of the classical configuration as far as to what you expect to see. So this one over here, what he's showing, and mathematically, he used a Chebyshev polynomial in order to get an equal ripple function for the impedance transformer. Going back to the idea that Wilkinson had as far as having the isolation resistors in a balanced configuration, in addition to the Chebyshev transformer, allows you to be able to build very broadband parts with equal ripple and very good performance. Like I said, the example here that Cohn had in his paper was for a 7-section divider that had a 10-to-1 bandwidth. And this sort of configuration is something that we use in the industry all the time. Like I said, this was a groundbreaking paper. This paper was written, by the way, just 2 years before TRM was founded. So it kind of puts it in perspective as far as to how closely TRM has followed this technology as we've developed as a company.
Okay, well, how does TRM work with these various types of dividers then?
Okay, so basically what TRM currently does is we have gone in there now and we have taken all these concepts from all these papers, and we've developed soft tools to be able to go out and actually be able to calculate this. Seymour Cohn's paper, for example, only gave exact solutions for 2, 3, and 3 section power dividers. It gave a table for approximate solutions for n equals 4 and n equals 7. What TRM has done is we've actually gone back into and derived and using the Chebyshev polynomials and the theory of small reflections, we have done exact solutions for any arbitrary bandwidth and any arbitrary impedance transformation from n equal 1 to n equal 15, which gives us a tremendous toolbox to work with for very, very, very broad impedances, as well as very different power splits based on the paper that was written in 1965. So this tool calculates all of those impedance transformers exactly for virtually any configuration that we need. The other thing also that this tool does is it automatically selects the optimum configuration in order to meet the bandwidth. For example, the number of sections that you need in order to be able to get the optimum VSWR bandwidth for any particular impedance transformation. The tool then goes one step farther and calculates what all the line widths would be in either strip line or microstrip, going back to their papers that were written back in the 1950s, as far as actually figuring out exactly what those impedances need to be. And then we've taken this one step farther, and then we've taken those dimensions and had them drive a layout in SolidWorks, and then using that layout in SolidWorks, imported directly into HFSS to be able to do an analysis of the circuit design. So this software tool, which we developed internally, can basically, from basic concepts of what is the frequency, what's your bandwidth, what's your physical size, we can have HFSS data on any one design in 15 minutes as a first pass. So it's a wonderful tool. Really, this is based on all the work that happened before there. All the math that's in those papers is all integrated into this tool, as well as lessons learned to be able to go out and actually be able to make good use of the technology that's been available.
Well, as always, Shaun, you've shared a lot of really good information. Would you like to maybe summarize it and just maybe encapsulate it in some way?
Sure. So basically, what the saying, as the saying goes, we're standing on the shoulders of giants. We have done some very good innovative work here. We certainly could not have developed, for example, the software tool that we have for derivation of these dividers without the work of Wilkinson, without the work of Cone. Very, very proud to say that those individuals contributed greatly to our success. Really, and I think what's important here is that no innovation happens in a vacuum. There's always something else going on. Keep your ear to the ground, find out what's going on, and you put two or three parts together, and all of a sudden you have some really great stuff. Part of what we've been able to do here at TRM is by applying the theory that was presented in some of these papers that I shared with you today, as well as modern computer tools. We can calculate exact solutions very rapidly, and then based on our lessons learned and design layout rules, we can reduce design variability because it's all being done by the computer, and create constantly theoretically optimized designs right out of the box, which really helps with our design time. So these are things that everybody says, well, gee, it's just a Wilkinson divider. Well, yeah, it is, but there's also an awful lot in the Wilkinson divider that you need to pay attention to.
Okay, and in other tech talks, Shaun, you've also identified some of the key TRM differentiators associated with the topic at hand. And I know you've alluded to maybe some of those here, but are there any additional unique things that would apply?
Sure. So, basically, as with, all of our TRM products, we like to work with our customers, and we want to provide the best solution possible. Like I mentioned in the past, TRM is a solution provider that also builds hardware. So basically what we like to do is like to work with our customers, find out really what their needs are, and then work to supply those designs that fill those needs, whether it's through robust mechanical packaging, some kind of a special testing, some sort of data that's required. Happy to be able to do that. In addition to go ahead and just, building parts to fill some needs. So really the big thing here is we like to work with our customers, find out really what it is you're doing. Even with something like a Wilkinson Power Divider, there are trade-offs to be made. Is output VSWR your most important parameter? Is input VSWR your most important parameter? Is amplitude or phase balance, or in some cases, isolation can be a driving parameter. We need to know those things. So we like to have those discussions with our customer to find out really what it is they're trying to accomplish, and therefore we can design a part that meets those needs.
Okay, and I suspect that when you talk about wanting to identify customer needs, That's part of what TRM offers by using the engineering hotline that we'll show in a minute, or maybe scheduling some of the engineering calls I've heard you speak of.
Yes, absolutely. So that's really one thing we want to do is we want to have an avenue to be able to speak with our customer, over and above the typical sales sort of interactions. Sales interactions are great, but at the same point, if a customer has a question, get a hold of us.
Okay, makes sense. So we did get a few questions. I think we have time for one. And this is a question that I find very interesting because, you shared quite a bit of the history about the power divider innovation, but it all took place in the 1960s. Have there been other major innovations since then?
Yeah, no, mathematically, not much. But what I will say is what has happened is the way we're building these dividers has changed dramatically. We're now using, we've advanced from strip line or the sort of strip line technology that was done back in the 1960s, which was basically taking multiple plates and putting them between multiple PCBs and bolting them together between plates. We now use multi-layered PCB technology, using plated through vias on PCBs in order to be able to go through it and create virtual ground walls and supplying a good positive ground. Interconnections between on and off the boards. A lot of those mechanical sorts of innovations have really helped us build a much more reliable, much more repeatable design than what was available back then. In addition to that, surface mount technology has removed a lot of the variable inductance that happens in a lot of these designs, and getting us back now to a truer resistor, for example, that runs in there for the isolation resistor on the Wilkinson. Theoretically, that those resistors want to have zero length going to the node, and if there's a wire sticking out of the resistor, it's going to add length. Back in the 1960s, that's how resistors were made. Going to a chip resistor or a film resistor certainly removes all of that length and gets you closer to the calculated theoretical performance. So it's a lot of good innovations from a manufacturing standpoint have happened since then. The good news is that the math that drives this is very well understood, and that really hasn't changed very much, really at all, since Cohen published his paper back in 1968. So from a math standpoint, not much change. From a manufacturing standpoint, a ton of change.
Okay, well, once again, lots of good information. Thank you, Shaun, and thank you to everyone who joined us today. If you are a customer and have more questions, or if you'd like to discuss details about a project or a program you have with one of our engineers, Shaun and the team would love to hear from you. Please feel free to call the hotline. The number is on your screen. If you're one of our, there's no cost for these conversations, obviously. If you're one of our field sales representatives, then your calls are always welcome too. And you can also submit questions directly through the sales rep portal. In case it's helpful, the next Tech Talk will be on Tuesday, February 15th, and the topic will be determined at that time. So thank you again, Shaun, and thank you, everyone.
Thank you, Paul.